We usually think of chemical reactions as a one-way street, right? Stuff gets mixed, something new gets made, and that's the end of it. But what if I told you that inside almost every chemical reaction, there's a constant, invisible, dynamic tug of war happening? Well, today we're diving deep into that battle, the amazing concept of chemical equilibrium. All right, so let's kick things off with a simple question. When a chemical reaction looks like it's done, has everything just stopped cold? The idea we learn in school is that reactants become products and the story's over. But in the real world of chemistry, the story is just getting interesting. So we're all familiar with irreversible reactions, right? You burn a piece of paper, it turns to ash, and there is absolutely no going back. That's a one-way trip. But it turns out most reactions are actually reversible. They can go forward, turning A into B, and they can also go backward, turning B right back into A. And that double arrow you see there, that's the secret handshake, the symbol for this chemical two-way street. And this brings us right to the heart of it all, the equilibrium state. The absolute best way to picture this is as a perfectly evenly matched tug of war. Okay, so here's the biggest takeaway. At equilibrium, the reaction has not stopped, not even close. What it really means is that the forward reaction and the reverse reaction are happening at the exact same speed. Just think about it. For every single new molecule of product that's made, another product molecule is breaking down and turning back into a reactant. It's a perfect dynamic balance where, if you were just looking from the outside, it would seem like absolutely nothing is changing at all. Right, so if this is a balanced state, how do we actually measure it? How do we know where that specific balance point is for any given reaction? Well, for that, chemists have a very special number. And that number is the equilibrium constant, which we call Kc. I want you to think of Kc as the official rulebook for a reaction. It's a very specific ratio of how many products you have compared to how many reactants you have after the system has settled into its happy place, that equilibrium state. And the cool thing is, for any reaction at a specific temperature, this number is always the same. It's a constant. So what does this Kc value actually tell us? Well, it's pretty simple. If Kc is a really big number, it means the balance point is way over on the side of the products. The reaction really, really wants to make products. If Kc is a tiny little number, the opposite is true. The reactants are heavily favored. And if it's somewhere in the middle, you've got a nice, healthy mix of both reactants and products just hanging out together in equilibrium. Now, that's all great for when a reaction is already at equilibrium. But what if it's not? What if you just mixed everything together? How can you predict which way the tug of war is going to pull to find its balance? Well, for that, we have another tool in our toolkit. Say hello to the reaction quotient, or Q. Now, here's the trick. It's calculated in the exact same way as K, but the difference is you can measure Q at any moment in time, not just at equilibrium. Think of Q as a snapshot. It tells you exactly what the ratio of products to reactants is right now, this very second. And this is where it gets cool, because by comparing our snapshot, Q, to the rulebook K, we can basically predict the future. If your Q value is smaller than K, it means you don't have enough products yet, so the reaction is going to shift to the right to make more. If Q is bigger than K, you've got too many products, and the whole system will shift back to the left. And if Q equals K, bingo, you're already there. The system is perfectly balanced. But what happens if we take a system that's already perfectly balanced and we poke it? What if we mess with it? Well, this is where a very, very famous principle in chemistry comes into play. This is Le Chatelier's principle, and honestly, it's like a cheat code for understanding chemistry. It basically says that nature is stubborn. If you take a system that's happy at equilibrium and you apply some kind of stress to it, like changing the concentration or the temperature, the system is going to fight back. It will actually shift its balance point to undo or counteract whatever you just did. Let's see this in action. Picture a system perfectly balanced. Now let's stress it out. We're going to dump in a bunch more reactant. According to Le Chatelier, the system has to counteract this. So what does it do? It speeds up the forward reaction to start using up all that extra reactant we just added, which in turn creates more product. And eventually it finds a new balance point, a new equilibrium. It's a beautiful, self-correcting system. Oh, and a quick but really important note about catalysts. A catalyst is kind of like a great referee who makes the game faster for both teams. It speeds up the forward reaction and the reverse reaction equally, so the system gets to equilibrium much, much faster. But, and this is the key, it doesn't change where that final equilibrium position is. It just helps everybody get there sooner.
Okay, so these principles might seem a little abstract, but they are happening all around you all the time. And one of the most important arenas for this constant battle for balance is in the one substance that covers most of our planet, plain old water.
You know, when you dissolve something like salt or an acid in water, it doesn't just sit there. It breaks apart into charged particles called ions. We call these things electrolytes. And the whole way they behave in water, how much they break apart and then get back together, is all governed by the rules of equilibrium. This is amazing. Even in a glass of perfectly pure water, a tiny, tiny fraction of water molecules are constantly splitting apart into acidic and basic ions and then immediately reforming. It has its own incredibly delicate equilibrium. And from that balance, we get a fundamental rule for any solution in water. The measure of its acidity, its pH, and its basicity, its pOH, will always add up to 14. That one simple number governs everything from the sour tang of a lemon to the harshness of drain cleaner. And this brings us to one of the most powerful and frankly life-saving applications of equilibrium, a buffer. A buffer is basically a solution that's been specifically engineered to be a master of Le Chatelier's principle. It contains a balanced pair of substances that can absorb little hits of acid or base, immediately counteract the change, and keep the pH unbelievably stable. It's like a pH bodyguard. So, why have we gone through all of this? Why does any of it really matter? Well, because this idea of a dynamic balance isn't just some dusty concept from a chemistry textbook. It is literally running the world around us, and more importantly, the world inside us. I mean, your very life depends on it right now. The pH of your blood is held in a razor-thin range by a delicate buffer system. If that equilibrium fails, you fail. Simple as that. In industry, chemists cleverly manipulate Le Chatelier's principle to squeeze out the maximum amount of product possible, like making the ammonia for the fertilizer that feeds billions. And in our environment, equilibrium dictates the very makeup of our atmosphere and our oceans. So I'll leave you with this thought. We've seen that chemical systems are resilient. They always fight to find their balance. But what happens when we push a huge global system, like our climate, so hard and so fast that it gets pushed too far out of balance? What then? Thanks for tuning in.